Okay, here on example 1, we're going to use angle side angle to prove that some triangles are congruent. We're going to complete a 2-column proof. We've got some given statements, so some given statements about our image. So for example, that angle BAC is congruent to DEC. So BAC and DEC, the two angles that they've labeled here by A and by E, are congruent. Okay, so that's just given. They're just saying that we've used a protractor or something, we've measured them, we know they're congruent. We know that they're same angle. The line BD bisects the line AE. So BD, this one, bisects AE, so it cuts it in half. Okay, it cuts it in half, which means that AC must be the same length as CE because that whole line's been cut in half. Okay, that'll be down here, one of our statements we'll make. We want to prove that the triangle ACB, so this triangle, is congruent to that triangle. Okay, so all we know so far is that these two angles are the same and that this line has cut AE in half. Okay, so the first statement we'll make, we'll just say what's already been given. So BAC is congruent to DEC. So those were the two angles are congruent. We just say that's been given. We don't need to give more of a reason than that. We just know it's already true. We already know that BD bisects AE. That's been given. Okay. Now the definition of a bisector, like I said a moment ago, means to cut something in half, which means that these two pieces, AC and CEE, those two pieces must be the same because they were just the two halves that were bisected. Okay, and the last thing we're going to say is that we know the vertical angles theorem. So if I go to a picture of vertical angles here, vertical angles are just defined as angles across from one another. I think maybe the word vertical comes from the idea that you can orient this image so that they're lined up straight above each other. If I turn the image, I could have the Y's above each other. And something being above something else is kind of like a vertical arrangement. So I think that's why they call them vertical. But in general, the vertical angles theorem says that the angles directly across from the vertex are congruent. Now, if I could show you that for a moment. Right here, what I've drawn is one horizontal line and then these parallel diagonal lines. And I've labeled that 1, 2, 1, and 2. Now, I'm going to show you that 1 and 2 are the same. Okay, the way I'm going to do it is this. First, we'll line them up over each other so that we can see that indeed, yes, those lines are lining up straight. So we have the same 1 and 2 here as we have here. Now, if I rotate this one, if I turn it upside down, I can still overlap it perfectly. I can still get it to overlap where the lines continue on. But now, rather than 1 and 2, I have 2 and 1. Okay, so 2 and 1 must be the same as 1 and 2, which means 2 equals 1 and 1 equals 2. They're the same angles, right? So if I flip this back around, you can see the original picture, and we can say that this picture does not look any different if I rotate it by 180 degrees. Okay, this picture stays the same, the labels just move, right? The 1 ends up on the top right, whereas before it was on the bottom left. Okay, so this is kind of showing that those vertical angles, those angles that we can line up vertically above each other, are always congruent. They are the same measurement. Okay, so they say that comes in handy here because angle ACB is the same as ECD. Okay, so these interior angles right here, these two vertical angles across from this vertex are congruent. All right, well, now we know two angles, right? So if we just look at this triangle on the right, we knew this angle. We knew this angle was congruent to that one, and now we know this angle is congruent to that one. So if the two angles are congruent to the other two angles, and their included side, so CE was the included side here, the side that's between this angle and this angle. So if that included side is congruent to this included side, then we're in good shape. So let me just real quick draw those trios. So the angle, side, angle, and the angle, side, angle. Okay, what we're saying is that that group of three features, the angle, side, angle, is congruent to the other angle, side, angle. And our ASA criterion has been satisfied. We have two triangles where there is a congruent angle, side, angle trio between the two of them, which means that necessarily this angle and this angle must be the same. This length and that length must be the same. And this length and this length must be the same. Okay, so we have now proven that they are congruent using just the fact that we knew that that trio, that angle, side, angle, was congruent to the other angle, side, angle. Once you have that angle, side, angle, you've kind of set in place what your triangle is. There are no other options for what your triangle is. As soon as you have this angle, side, angle, it must be this triangle because these lines need to match up at just a certain point up here. Okay, so if this triangle has to be this one, and this triangle has to be this one, well, they're going to be the same triangle because the things that forced us to define the triangle were the angle, side, angle. Okay, so that would be your proof for example number 1.